Okay, I'm continuing from where I left off. So I was talking about quantum homomorphisms and measurement graphs. And so the measurement graphs are fairly difficult to visualize, and I don't spend much time trying, but one case which is fairly easy. So if the index of our measurements is 1, so in other words, if they're the quantum homomorphism 0-1 matrix, and then it's easy to verify that a graph is isomorphic to the MY1. And basically that any measurement of y assigns standard basis vectors to each vertex of y. And the rule is that the two standard basis vectors are adjacent if only if u is adjacent to v. And being adjacent means u is equal to v. So that's the best and easy exercise if you're not sure about that proof. Now, the couple of things that are useful if we have two measurements on graphs x and y respectively, and then we can define the Kronecker product or tensor product to be the set of tensor products. Now, the claim is that's a measurement. Okay, it's fairly clear. It should be immediate. Each of those things is a projection, and they sum to the identity. So it's a measurement. It's a measurement on the vertices of the Kronecker product of x and y. So that should actually be, I think I'll make that a direct product. I like to be a bit more precise. So I'm dealing with the graphs. It's what we normally call the direct product. So a consequence of this is that the direct product of the two measurement graphs is isomorphic to a subgraph of the measurement graph x times y. Now, I'm going to be leaving a number of these things as exercises because they're reasonably straightforward and you'll learn more by doing it than watching me play around with it. But so in a sense, you can embed the smaller measurement graphs and the bigger measurement graphs. We'll come back to that later on, perhaps. Should be so if we have quantum homomorphisms from Z to X and Z to Y, then we have graph homomorphisms from Z to the measurement graph MXD and to the measurement graph MYE. And so we have a homomorphism in that case, a graph homomorphism from Z into the direct product of those two things, which admits, in turn, gives you homomorphism into this guy. Oops, I didn't want to do that. And so you've got a homomorphism from Z into a measurement graph of X times the direct product of X and Y. And so therefore there's a Q homomorphism from Z into X, Y. Now, when I talked about direct product before, the key fact there was if you had homomorphisms from Z to X and Z to Y, then there was a homomorphism from Z to X times Y, which is in some sense compatible with the information we already had. And so that told us that the direct product was the so-called categorical product for graphs. And so what this tells you, if you care, is that if your category consists of graphs and quantum homomorphisms, the product is just what it used to be. It's just the direct product. Okay. So that's a connection between the two. So it hasn't changed. And the sort of dual to that is the following statement. If we have quantum homomorphisms from X to Z and Y to Z, then there's a quantum homomorphism from X to N, Y to Z. And again, I'm leaving the proof that as an exercise, but again, in the category of graphs, X union Y is the joint union of X and Y is the sum of X and Y. And so it shows you that X union Y is also the sum of the quantum category. So there's a lot of similarities between the two setups, and there are also differences as we'll see as we go along, but some products behave as expected. Now, this lemma just says that the graph in this measurement graph Q homomorphs are equivalent. So two graphs X and Y are homomorphs equivalent if X arrows Y and Y arrows X. There's homomorphs from X to Y and from Y to X. That's just the definition. And so replace homomorphism by Q homomorphism, you get Q homomorphism equivalent. Now, the homomorphism equivalent classes have a nice class of minimal elements, which are called the Corsa graph. We don't get anything like that, as far as we know, in the quantum case. But anyway, let's leave that. So the claim is that these two guys are homomorphism equivalent, and it's just playing little games with what we have already. So we have a homomorphism from MDX to itself. This is a graph homomorphism. It's just an isomorphism. So if you have a homomorphism into the measurement graph of X, then you have a quantum homomorphism from MD of X into X. Okay. Now, certainly you have a quantum homomorphism from X to X because the classical homomorphisms are quantum homomorphisms. And so therefore there's homomorphism from X into MDX. And so therefore you get the equivalence. Okay, so it's a sort of thing that you stare at it and it looks completely straightforward, but whenever you try and reconstruct it, you suddenly find it takes a few tries to get this sorted out. But anyway, so these two graphs are homomorphism, Q homomorphism equivalent. There are very few cases where you can say anything useful about the structure of MDX, but it's there, and it does tell you that you can translate questions about quantum homomorphisms into questions about graph homomorphisms into infinite graphs. Okay, so I want to go now and talk about some operations on homomorphisms, these on quantum homomorphisms, and there's a number of useful ones which we need to discuss. Now, there's an important point which I need to make here. If we have a quantum homomorphism, then the elements as the entries in the matrix we write down the d by d projections, and so they generate a matrix algebra. And if this algebra is commutative, then the quantum homomorphism is classical. Okay, and so the physicists aren't interested. If it's not commutative, then it's not classical. There's a tendency to say it's a quantum homomorphism if it's not commutative, but that's a bit bad because you still want the homomorphisms to be quantum homomorphisms, so it's not consistent with their usage. So and so we're interested in quantum homomorphisms where the algebra generated by the projections is not commutative. And these would be the non-classical case. Now, I'll probably make this into an exercise. The point is, if the algebra is commutative, then projections are normal. And if you have a bunch of computing normal matrices, you can simultaneously diagonalize them. And so you can make a change of base or something, your underlying copy of C to the D, and convert each of your projections simultaneously to a diagonal matrix. Now, these diagonal matrices give you the eigenvalues of projections, which are 0 and 1. So you get a bunch of diagonal matrices with ones and zeros. And the claim is that it'll be easy to see how to get that. Well, we'll describe how to build up that sort of homomorphism shortly. Okay. The other comment I should make is there are actually two flavors. When you're dealing with quantum homomorphisms and projections, there are actually two flavors. I'm taking the easy flavor where my projections are all elements of some matrix algebra of finite dimension. Now, if you choose to, and physicists will do this, you can, instead of taking it coming from a matrix algebra, you could take it to be coming from a so-called C-star algebra. I won't be going this into all, but there are two classes of quantum things, and they're not equivalent. On the other hand, we don't really understand either of them, and so I'd say that it's nice to start with what's on the face of it should be the simpler case. So I'm assuming throughout not dealing with everything's finite dimensional or my blocks are finite dimensional in my homomorphisms. Okay, so the two operations I want on quantum homomorphisms, or actually three. First is what I'm going to call the direct sum, and basically we have two quantum homomorphisms, curly P and curly Q, and we take the ij entry of our new quantum homomorphism to be the direct sum of the ij entry of the two homomorphisms we started with. So you get the direct sum, just to remind you, is just a block. Direct sum of A and B is the block diagonal matrix A0, 0B. And the understanding is A and B are square. So that's it's standard terminology. It's not that familiar. And so we've got a definition that the ij entry of the direct sum is just the direct sum of the ij entries. And again, it's a straightforward exercise to show this is a quantum homomorphism, and there's classical if only if the inputs are classical. Okay, so we can form direct sums. Now, this turns out to be quite useful, but I'll come back to that. The other operation we have, well, we have quantum homomorphisms. Now, certainly with graph homomorphisms, we can compose them. So we have homomorphism F and homomorphism G, then we can form the composition F of G, or G of F, actually, is the way you normally think about it. And so you can compose them, okay, and they're associative. And this is what always makes graphs and homomorphisms into a category. Now, up to this point, I said nothing about that. I've defined a quantum homomorphism, but it's not clear how we combine them. And this is the rule here. So if I have quantum homomorphisms from X to Y and Y to Z, then I'm going to define P star Q by the following rule. So you can think of this as just multiplying the matrix of P times the matrix of Q with one wrinkle. Instead of using a matrix multiplication, you're going to use tensor multiplication. So that's what's happening. So this is exactly the formula for the product of two matrices, except we're using the tensor product instead of the regular product. Okay. Now, this is called, for reasonably good reasons, the co-product of P and Q. I promise not to go into that. So the point is we don't want to call it a product because the output is in some sense higher dimension than the input. Okay. So and so we're normally with a product you take two big things and you get something simpler. In this case, it's reverse. So it's actually the reverse of a product. Now, if P and Q have index 1, if the projections are all 1 by 1, then this is just the usual matrix product. So we have at least that in our favor. Now, again, something else I'll leave as an exercise then. If we have homomorphisms, quantum homomorphisms from X to Y and Y to Z, then the co-product is a quantum homomorphism from X to Z. Okay. Again, that's reasonably straightforward, and I'll be putting that down as an exercise. The other thing which I'm going to dump on you is the fact that the co-product is associative. Okay. Now, the only issue there is you have to identify, let's get some colors. You need to identify things like A tends to B, A tends to. Now, as far as the exercise is concerned, you can be sloppy and pretend those two things are equal. Technically, they're not. There's an isomorphism, but you don't need to worry about them. I mean, so all you do is you go and look up something on McLean somewhere and then quote it and throw a citation at it. So you treat these as being equal. Technically, they're isomorphic. Okay, but tensors are complicated enough. So if you take these as being equal, then the associativity is easy. And then there's this mistake there. And the co-product is classical if and only if the inputs are. Now, so automorphisms are graphs of homomorphisms. Okay. And so if I have two automorphisms graph, I can form their direct sum. And that will be a quantum homomorphism. It won't be a permutation anymore. Okay, but it's still viewed as a classical. It's still classical. So when we talk about quantum homomorphism or quantum automorphisms being classical, we're not assuming that they're permutations. We're assuming that they're direct sums of permutations. Okay. I should say practically everything that I'm doing in these lectures is in the paper by Dave Roberson and other and possibly with other people in his thesis. I don't think the direct sum is in there, but the co-products are in there. These facts I'm throwing at you, they're all in work of Dave Roberson. So the only thing different is the arrangement and the mistakes. Okay, so yeah, so I've introduced the direct sum and the co-product, and I'll be getting you to prove that the direct sum and co-product of quantum homomorphisms are quantum homomorphisms. And so the other point is that there's, if you've got a quantum homomorphism of index D and another quantum homomorphism of index E, then their co-product's going to have index DE. And if you're bored and nothing better to do, you could just take the co-product of itself, and so you can build up quantum homomorphisms of very large index very quickly. Okay. So the set of all quantum homomorphisms is sometimes called a quantum group. Now, I won't be going into that at all. I will say that the word group there has no meaning. It's certainly whatever it is, it's not a group. And so it's a more complicated structure. And this is actually goes back to what I was saying before about the C-star algebras and so on. So the I'm not going to give a definition of what they call the quantum group attached to a graph. So we're saying we have a well-defined process. We have graphs. We have quantum homomorphisms. And so that will give us eventually quantum Waterloos and quantum colorings, and so we can work with these and ask questions about these. Okay. Now, some people somewhere are interested in the quantum group, but I've found no reason to go down that rabbit hole yet. So, okay. Now, but again, just bear in mind that when we're talking about classical, it doesn't necessarily, classical may not mean exactly what you think it means. It includes things which you wouldn't have normally considered. Okay, but and that's free. And the other point is worth bearing in mind is that the index of your quantum homomorphisms on the whole tends to be large. And you'll see some of this coming up in the next result. But so that I mean, index 1 is just the standard, the bog standard quantum, bog standard homomorphisms things. Okay, so index 1 is okay, and index 2 is almost as trivial. Okay, so just as sort of a understanding where you are, in general, the index tends to be large. It might be like the index might be greater than the number of vertices in either graphs involved. Okay, now it is what it is, but it's just that. So the index tends to be large, and the small index cases are a bit special. So I want to give a proof of the following result. The result's due to Robeson again. The proof is not. But so we got a quantum homomorphism from X to Y with index D. So D with E matrices, and the assumption is that we have a subgroup of G, subgroup G of automorphisms of Y. Okay, and acts transitively on Vy. So the simplest case, one of the simple cases would be to think about where Y is a circulant. Okay, and then the cyclic group of order n acts transitively on the vertices. Okay, so we're having our assumption. Now, we're going to apply this because quite often our target graph is going to be the complete graph. And that's transitive. So everything we do involving a complete graph, we can apply this result to. So the result says there's a quantum homomorphism if you've got a quantum homomorphism from X to Y with index D, and if there's a group acting transitively on the vertices of Y, then there's a quantum homomorphism from X to Y such that each entry has the same rank and the same index. So you can make all the ranks equal. Now notice that the rank is going to be size of your target graph times D. So like I said, the rank can be big and the index can be big. Okay, now it's not too hard to see this is a quantum homomorphism. I waste a lot of time trying to get the formula right for the rank and index. But the way to think about this is if you have a, let me actually do it here. Is I have a quantum homomorphism. No, one to pen. Okay, okay, no, I can't do for that. Now, first thing is that don't really need this picture, but the entries in each row sum to the D by D identity. And they're D by D matrices, just we're taking the base case. Okay. Now, if these guys each have rank R, they're pairwise orthogonal. And so the sum of pairwise orthogonal projections of rank R, well, the sum of M pairwise orthogonal projections of rank R has rank M times R. So we're assuming we're going to say this is M, this is N. So the point is that if we assume, so we get that the rank, well, we have that size of Vy times R is equal to, well, it must be equal to D. Okay, so the rank divides the degree, which makes sense because you've got D by D permutation projections. They can't have rank greater than D. Okay, but the degree is a multiple. There's nothing really stopping R being 1. The degree is at least the size of Y. Now, I see that the case where the entries have rank 1 is of some interest in some cases. So it's not like when they were saying that when D is equal to 1. So if R is equal to 1, you can still do quantum things. If D is equal to 1, you're doing classical graph theory. Okay, so I just want to emphasize, this is emphasizing my point that, and so I've got statements about the rank of the index there, but I realize eventually they're a triviality in a certain sense that if you know that the rank is constant, then you must have that relation. And so everything goes as said. So I'll outline the proof. So the point is, if we have a quantum homomorphism from X to Y, we can compose that with an automorphism of Y. So I'm going to take a subgroup G, the automorphism group, and I've got some element sigma in G. Then my homomorphism is going to be, I apply the quantum homomorphism, and then compose that with the group automorphism. Now the result will be a quantum homomorphism from X to Y. It won't be equal to the previous one because basically what you're doing is you're shuffling the columns of the quantum homomorphism using the group element little g. But it's quite clear if I have a quantum homomorphism and I permute the columns, what I've got is still a quantum automorphism. Nothing's broken. Okay, so let me be original and denote this matrix by p to the sigma. Okay, so now I've got a choice of sigmas, then I take the direct sum of the homomorphisms p to the sigma for sigma in my group G. Now it's a direct sum, so that's a quantum homomorphism by the exercise I listed before. And each entry is the direct sum of the same projections. In fact, the number of times the rejection occurs will be equal to the size of the stabilizer of the vertex of the group. We don't really need that, so I'm not going to say anything more about it. But you get, so that what I am saying is that you may have some repetitions involved in the, so each entry of this guy is block diagonal, and the blocks are just projections. Okay, coming from P. Okay, so by using a direct sum, we get a proof of this result. So that tells us if we're dealing with homomorphisms to a vertex transitive graph, then if we choose to, we can assume that each projection has got the same rank R. And this is a convenience in a number of cases. Okay, so this is just expanding on what I just said. Okay, so that gives us two operations. We have a direct sum operation and the co-product. I mean, the co-product is quite important of the two if you had to choose one, but both can be useful, but the co-product will come up in various forms. And in particular, the co-product underlies the fact that it's how you compose two quantum homomorphisms. The point is, as I said before, a quantum homomorphism is not a function from the vertices of X to the vertices of Y. So if I have a quantum homomorphism from X to Y and from Y to another from Y to Z, I can't just say, well, I take the vertex little y and big Y and apply the second homomorphism to it. So I have to do something different. And what you do is you use the coproduct. Now, if this makes you unhappy and an actually read reaction, you just got to get used to it because that's what works. Okay, so this is one of the differences between the category of quantum homomorphisms and the category of graphs. Okay. Anyway, now I want to, well, in a certain sense, there's another operation on the quantum homomorphisms I want to use, and that involves things called fractional isomorphisms. Now, this is just straightforward algebraic graph theory, insofar as algebraic graph theory is straightforward, I guess. So the and I said fractional isomorphisms, yeah. Okay, so the stuff I'm about to describe was first it was introduced by graph theorists, not in the context of anything quantum. Okay, and what they were, well, what part of what they were attempting to do was to generalize the idea of a permutation of an isomorphism, of a permutation. Or an isomorphism to do graphs. So X and Y are graphs with respect to adjacent geometrices A and B. Now, a matrix S determines a fractional isomorphism. We should have made that prettier. From X to Y. What am I doing here? If A, it's doubly stochastic, each row and column sums to 1, and B, A applied to S is S times B. Now, we will see, and it's not entirely trivial, but a doubly stochastic matrix is necessarily square. Okay, just as a reference. Okay, so that means that A and B will have the same, so the graphs X and Y are the same size. So we're defining fractional isomorphisms. I don't think that there's a reasonable definition of fractional homomorphism. I don't know one. Okay, but this is a fractional isomorphism. Now, so examples, well, the simplest example would just be just be a permutation. Permutation matrix is doubly stochastic. Okay, and so every permutation matrix gives rise to a fractional isomorphism. Now, in a sense, the question is, well, what else can we get? Well, I mentioned for permutation matrices. Somewhat disappointing example, if you X and Y are k-regular graphs on n vertices, then AJ is equal to JA, both are equal to k times J. And so 1 of n times J is a fractional isomorphism. So we've solved the fractional isomorphism problem for regular graphs. If they have the same number of vertices and the same boundlessly, then they're fractionally isomorphic. Okay. So well, it is what it is. The third example I got here is if I've got two fractional isomorphisms from X to Y and Y to Z, then their composition is a fractional isomorphism. Okay, and so particularly the fractional automorphisms of graphs, I'll write it down here. The fractional automorphisms of graph form a monoid. It's associative multiplication that is an identity. Okay, so you have a monoid of fractional automorphisms of the graphs. Now, nobody ever does anything useful with monoids as such, but it's a useful language, and so there's no reason not to use it. So we can multiply them. So to that extent, they're behaving like automorphisms and regular automorphisms. Okay, now the first question, well, it's fairly clear from this example that fractional isomorphisms aren't going to exhaust your possibilities. But even if we sort of stay away from the regular case, well, we have the automorphisms. Could there be other stuff? And that's what we talk about. Now, I mentioned that doubly stochastic matrices are necessarily square. Now, my argument for this, it took me some effort, and I suspect I may have made a meal of it, but we'll discuss it anyway. There's some terminology if I need. So if I have a doubly stochastic matrix, I can view it as a weighted adjacency matrix for a directed graph. So this will be a directed graph with loops and parallel edges, loops and edges. There won't be any parallel edges. It's just loops. So loops with weights attached and arcs with weights attached. Okay, so that's it. So we have a directed graph now. So the point is, I have a doubly stochastic matrix. There's an underlying directed graph. Now, for directed graphs, there's two notions of connectedness. One is that the directed graphs are weakly connected if the underlying graph, where you ignore the directions, where you put in the opposite of each arc that's not already there, that underlying graph is connected. So it says that if you've got two vertices A and B, it is possible to get from A to B. It may not be impossible. It may not be possible to get back again, but you can at least get from A to B. So that's weakly connected. And it is strongly connected if for each pair of vertices U and V, there's a directed path from U to V. And in this case, for instance, that allows you a directed path from U to V, and there'll also be a directed path from V to U. So that's strong components. Now, when you're trying to do algebra, these weak components are in nuisance. Okay, and so you'd rather deal with things that are strongly connected. So the one way this is strongly connected is described if you view the directed graph as a sort of street map with a one-way street there. You can get from any place in the city to any other place in the city without going the wrong way down a one-way street. Okay, so we've got two notions: weakly connected and strongly connected. And what we're going to show is that we don't have to worry about the weakly connected stuff. That everything we see will be the connectedness will be equivalent to strongly connectedness. So to do that, I need to translate these terms into matrix theory. And so an n-by-n matrix is reducible if it contains a submatrix of order m by n minus m with all entries 0. So, well, permutation equivalent to such a thing. So the p thing, oops, it's terrible. We have a submatrix of this form with A and C squared. And so a matrix like that is reducible, and anything you get from it by permuting rows and columns is still so reducible. But I'm going to, okay. It's decomposable if it's permutation equivalent to something of this form, where you have an n square. Now, if you'd done some representation theory, then you've seen irreducible and then equals representations, and the usage is the same. If you haven't, just ignore that remark. What I really need is, well, reducibility corresponds to not, if the matrix is reducible, then the digraph is not weakly connected. It's not strongly connected. Okay, so actually, I might write that in. Any questions at this point? Okay. And so, well, here
is that an m times n minus m?
Sorry?
Chris?
Yes.
Is that an n, n times n minus m, or an m? I can't read.
That's
of submatrix of order.
Which page are we on? This page or next?
Yes, this one. So it contains a submatrix of order.
That's an m by n minus m.
Thank you.
That's this guy. Oh my God, I can fix that one here, I guess. That's any better. Okay. So this terminology it's all quite standard, and it's a bit more than I actually really need. What I need, in a certain sense, might have been simply just to do this, is to say if S is doubly stochastic, it's square, and that each weakly connected component is strongly connected. So in other words, the two notions of connectors don't differ, which is nice, so we don't have to fuss about it. So if it's doubly stochastic, it's square, and each weakly connected component is strongly connected. Okay, and that's a sketch of the proof just there, but we'll go into it. So we assume that suppose we're not strongly connected, okay? So we're going to assume now that I got this block here of order m by n minus m, okay? And I said, and I'm assuming so A is m by m, and C is, and everything, and C is, actually I haven't made any assumptions about C. What I'm proving is that I'm going to prove, let me just go on and do it. The first thing is that the sum of each column of A, well, the sum of a column of S is 1. It's doubly stochastic. So the sum of each column of A is less than or equal to 1. Nothing clever in that. Okay, and so that means that the sum of the entries of the A, since is at most m. Okay. On the other hand, the sum of the rows of any row of S is 1, and so the row sums of A, each row of A sums to exactly 1. So the column something to something less than or equal to 1, and the row sum to something equal to 1. And by the fundamental theorem of accountancy, the sum of the row sums is equal to the sum of the column sums. Okay, so we have, on the one hand, we have this, and on the other hand, we have this. Now, anyway, they can both be true is we must have equality here, and that implies that each column of A sums to 1. So B is 0. Okay, so I mean, there's some packaging needed, but that's the key part of the proof. So now from that you deduce that you may have to, you basically imply induction and assume that you start with the sort of smallest component, do it component by component, but I'm not going through all that. But so the point is that this argument tells me that if I have this structure, then A is square, well, and B is 0. And so each block of my matrix is square, and so the entire matrix is square. Now, I suspect that's actually that I did have more of a mess of this when I tried it the first time, but I don't think I can simplify that. Okay. Okay, so now if R and S are doubly stochastic, so is their product. I mean, if you just say if S is row stochastic, then S times 1 is 1. And so it's easy to see that RS times 1 is 1. And similarly, 1 transpose RS is equal to 1 transpose. So the product of fractional isomorphisms from the monoids I noted before is contained in the automorphism group. The other point is that this set of fractional isomorphisms is a convex set. And that's what the next argument is saying. So if we have fractional isomorphism here from A to B, second one from A to B, and you pick a scalar, real scalar between 0 and 1, then you get this, and from which it follows that what that implies is that this is a fractional isomorphism. Yeah, I got that right way around. Okay, so this is a fractional isomorphism. So the convex combination of two fractional isomorphisms is a fractional isomorphism. And so the set of fractional isomorphism contains all convex combinations of automorphisms. Okay. So it's a convex polytope. It's a solid body. Okay. The permutation matrices belong to this polytope, and they are vertices of this polytope. Okay. Okay, they're not. There's a half spaced that contains that point and nothing else in the set. So the permutation matrices are the vertices are vertices of the convex holotope. And the question that people were interested in was, well, under what conditions that they were the only vertices? So the idea is in that case that your isomorphism structure is a bit simpler, that everything was just a convex combination of automorphisms. And so the term that was introduced is if the only vertices of the holotope come from permutations, then the graph is said to be compact. This has got nothing to do with the topological meaning, as far as I know, and it's a very strong condition, and it probably won't come back to us. But I do need. We will see fractional automorphisms arising very shortly. Okay. So this is some graph theory background. There's papers by Tim Hofer and others. There's a reasonable literature now, but so okay, yeah, right. So before we do that, I need to establish a connection between fractional isomorphisms or fractional isomorphism and equal partitions. Now, if I have a permutation matrix which commutes with a group, then, or if I have more generally, I have a group of automorphisms I have a group of automorphisms as a graph, then the orbits of that group form an equitable partition. So if I have a permutation, I can look at the group it generates, I get an equitable partition. And this is in some sense one place where equitable partitions, well, it wasn't the first place, but the second place where equitable partitions arose in context with computing automorphism groups. Okay, so groups of automorphisms give rise to equitable partitions. Now, what we're going to prove now is that we can get equitable partition not just from automorphisms, but from fractional automorphisms. And this is going to matter to us because we're going to get fractional automorphisms from quantum isomorphisms. And so this will be meaningful at that point. So I'm going to use script f of x comma y to denote these set of fractional isomorphisms from x to y, and I'll abbreviate f of x comma x to f of x. And yeah, I did prove it. So the first comment simply is if R is a fractional isomorphism from x to y, then R transpose is a fractional isomorphism from y to x. So this is the analog of the group theory result that if you've got an isomorphism given from A to B given by permutation matrix P, then the isomorphism B to A is given by P inverse. But since it's permutation matrix P inverse is equal to PT. So this is generalizing something that you know. The other comment I just throw in here is the note that since R is W stochastic, so is R transpose. So this product is W transpose, and ditto for this. Now, okay, so I want to prove this claim. It's something nice and relaxing. If R is W stochastic and AR is equal to RB, then I'm just going to take transposes. So well, I haven't taken transpose yet, but I get R transpose A is equal to this because A is symmetric, and that's equal to this just by taking the transpose of that. And then B is symmetric, so you get R transpose A is equal to BR transpose. And so that tells me that if R is a fractional isomorphism from x to y, then R transpose is a fractional isomorphism from y to x. Not really sure I need this. Well, from this equality, I get multiplied left by R, I get RB R transpose equals to, I've got it back to front here somewhere. Okay, no, I'm going from here. I put an R transpose on the left, both sides here, and I get this. And then I notice this is symmetric, and this is symmetric, and this is symmetric, and the product of two symmetric matrices is symmetric if only if they commute. So we get that in this context that A commutes with R transpose, and B will commute with R T transpose R. I'm not sure I'm actually going to need that, but it's and this is a W stochastic matrix. It's symmetric, and it commutes with A. Now I want to construct equitable partitions. And I said that the right way to think about equitable partitions is not in terms of the commentary or definition about counting edges from this cell to that cell. It's in terms of invariant subspaces. Okay. So in particular, what I want to do is to construct a projection that commutes with the adjacency matrix, and then deduce from that I've got an equitable partition. So the theorem is that if we have a fractional isomorphism of X, then the vertex sets of the strong components of the directed graph determined by R are the cells of an equal partition of X. If you sort of translate this out properly, you will see this would work for a permutation as well, but we don't have to think about that. That will follow anyway. Now, the proof of this requires the Perrin-Frobenius form theorem, or consequence Perrin-Frobenius theorem, and this is a little bit more general than the version of Perrin-Frobenius theorem that I stated earlier. I'm not going to apologize, so I'm just going to use it. Okay, there's lots of references to it, and you'll see exactly what I'm using. Okay, so what I'm going to need to use is that if I have a non-negative real matrix and its underlying directed graph is strongly connected, then the spectral radius of the graph, or the spectral radius of A, is a simple eigenvalue. Now, the spectral radius is the maximum absolute value of an eigenvalue. But the spectral radius is positive, and so this is saying that the largest eigenvalue is positive. So there's an eigenvalue rho, which is positive and greater than all the others. There could also be an eigenvalue minus rho, in which case it turns out that something's going to be bipartite, but we're going to be able to ignore that case. I don't think it doesn't bother us. So the point is that the Perrin-Frobenius theorem tells us that the largest eigenvalue, in this case, that the largest eigenvalue is positive, okay, and that it's simple. Okay, and that's important. Okay. So that's the consequence of Perrin-Frobenius that we're using. And so now I want to prove the theorem. So we have R as the, well, there's a theorem back here where R is our fractional isomorphism. And so, or automorphism, so it commutes with A. And since R is doubly stochastic, the weak components are strong. And so the spectral radius of each component has a simple eigenvalue. Okay, so how does that help me? Well, each row of R sums to 1. It's doubly stochastic. And so that tells me that if I have just think about the strongly connected case, I've got this doubly stochastic matrix underlying graph strongly connected. The all ones vector is an eigenvector, and its eigenvalue is 1, and that's the spectral radius. Okay, so I know the eigenvalue is simple. So I know 1 is a simple eigenvalue of each component, and that the corresponding eigenvector is just a constant vector. And so it follows that the one eigenspace of R is spanned by the characteristic vectors of the components. These are 0, 1 vectors. And if there are k components, there'll be the eigenvalue 1 multiplicity k. Okay. And so now because the eigenvalue is simple, because 1 is a simple eigenvalue, there's a polynomial in A which is equal to the projection onto the one eigenspace. You just choose a polynomial which vanishes on all the eigenvalues of A except 1, scale it, and then you discover that that polynomial evaluated in A is going to be your ones matrix. Okay, I can't use spectral decomposition because my matrix is not necessarily symmetric. I could probably go over and use the RR translates, but my point is that I'm getting a spectral idempotent. Okay, so I'm in a situation where by Perrin-Frobenius I can construct a spectral idempotent as a polynomial in A or in R. Okay, polynomial in R. Okay, and I don't know what happens to the other eigenvalues. I make no claim. So I'm getting a sort of a weak version of spectral decomposition. Okay, so that means that the projection on the subspace is going to look like this. Oops. it's going to be block diagonal, and each block is a scaled multiple of j. Now, this is the this matrix, the normalized characteristic matrix of the component partition. Okay, and since it computes with A, the partition is equitable. This shows that the Perrin-Frobenius theorem this is a somewhat unusual usage of the Perrin-Frobenius theorem, but it's there to be used. And so we have that the partition is equitable. And we'll see how that helps us as we go on. What's the time? No, that's right. I'll stop there. Perfect timing.